Hello, I'm Itzik Lapidot, and I'm happy that you are all with us at the 12th AFECA Speech Processing Conference. It is the second year we have a Zoom conference. Hope next year to see you all face-to-face, to chat, eat, and smile together, hopefully without masks. This year, we concatenated both the Speech Processing Conference and the Speech Technologies for Healthcare Conference. I'm sure you will find that the program of this year is very interesting. If you want to forward a question to the speakers, you have to send it by chat if they are not in the studio. And we let you send the questions for the limited time. Before I will invite Professor Werner Aronson to say a few words, I want just to inform you that Israel will host the 2024 Interspeech in Jerusalem, thanks to Professor Sharon Ganot from Bar-Ilan University that shared the chairing with me, Galit Shimshoni from Ortra, and our local and international committees. And now I want to invite Professor Werner Aronson, head of ACLP and chair of the Speech Technologies for Healthcare session in this conference, to say a few words. Please, Vered.
Good evening, everybody, and thank you for joining us today. Indeed, we hope that this conference will be a physical one. However, technology has its merits, and we have this year a wider audience from many countries, so we open up for a wider participation. And again, every crisis has its opportunities, and we've seen this year how technology rose and enabled new solutions for the pandemic and its consequences. And speech technology played its role, where all communication became digital in lectures and physical and in conferences, and definitely in healthcare, on which we'll talk in the next part of this conference. So again, welcome all, and enjoy the next couple of hours with 5 lectures on the development of speech processing in the past year. Thank you.
Thank you, Vered. And now I'm excited and honored to present our keynote speaker, Professor Helen Meng, which is in our International Committee for Interspeech. Professor Meng is one of the leading researchers in the world in different areas of speech technologies. We do not have the time to cover all she did and does. Professor Meng is Patrick Hyun Ming Professor of Systems Engineering and Engineering Management at the Chinese University of Hong Kong. Her research interests include AI for speech and language technologies and support multilingual and multimodal human-computer interactions. Professor Meng is editor-in-chief of the IEEE Transactions on Audio, Speech and Language Processing, ISCA board member, and much more. Professor Meng received many awards, and the title of her talk is Advancing Technologies, Equity in Speech and Language Processing. Please, Helen, do you hear us? Are you with us now?
Yes, can you hear me?
Yes, we can hear you well. We are so happy that you can be with us, and I'm sure all the audience will be excited from your talk. Please, the stage is yours.
Thank you, Dr. Lapidot. Please let me share my screen. Please let me share my screen. Let's see. Please let me share my screen. Hello? Hello? Eyal, please let me share my screen. Okay. 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 Can you hear me? Hello? Okay, great. Okay. Thank you very much. Thank you very much to Dr. Levidoff and also to the crew. So good evening, ladies and gentlemen. I would like to start by thanking the organizers of the Africa Speech Conference for this very kind invitation. And it is indeed an honor for me to be able to share some of our recent research work with the audience today. I'm Helen Mang from the Chinese University of Hong Kong. And also last year, I helped our university set up a new research center, which is called the Center for Perceptual and Interactive Intelligence. And it is located in the Hong Kong Science and Technology Parks. So today, my talk is entitled Advancing Technological Equity in Speech and Language Processing. So this is our team, and the work that I will be presenting is contributed by different members in our team. I have collaborators. I have two collaborators. They're both professors. In Hong Kong, I collaborate with Professor Xunying Liu. We come from the same department. And in Shenzhen, I collaborate with Professor Ji-Young Wu, and he is the co-director of the Tsinghua CUHK Joint Research Center for Media Sciences, Technologies, and Systems. And within this team, there are 16 students and staff who are under my direct supervision. So this is the outline of my talk, and I'd like to also acknowledge the support from our various funding agencies and sponsors. So communication by speech and language is quintessentially human. The speech signal carries rich information about what we mean, who we are, how we feel, and also encodes subtle information about our education, our health, our cognition, etc. And this communication is influenced by a greater or lesser degree by the cultural background and communicative context. Now, state-of-the-art speech and language technologies have become very, very advanced, and we can see that our technologies have come of age and are ready for prime time. However, we're also mindful that the performance of these state-of-the-art technologies will significantly degrade in face of certain types of speakers and communicative contexts. These are cases that are sometimes referred to as atypical speech. And in fact, this is speech that is underrepresented by the training data that went into the technology development. So atypical speech can refer to accented speech or disordered speech or child speech, older adult speech, etc. The technological inequity for these specific users and usage contexts is a disadvantage, but it is remediable. The problem lies in data scarcity and data sparsity, and these are the data that goes into training our models and algorithms. For example, it is very difficult to find speakers to donate disordered speech data. And even if we are able to find such speakers, oftentimes their conditions will cause them to quickly get exhausted while they're recording for us. And also, the problem is exacerbated by high data variability due to the etiology of a disorder or the different levels of severity. Also, in another context, we can see broad ranges in regional accents, also with different gradations between light to heavy accents. And also we can see continual changes, biological changes, such as due to aging, and also progressive pathological changes, such as due to neurocognitive disorders or dementia. So in this talk, I'm going to share the experiences from our team in working with dysarthric speech, older adult speech, where sometimes the individual may also have cognitive impairment, accented speech, and code-switched speech to accomplish different tasks, including recognition and reconstruction, speaker diarization, mispronunciation detection and diagnosis, as well as speech synthesis. We have been using available data in the field as well as collecting our own data for research. And all these investigations face the challenge of data scarcity and data sparsity, so we will describe different approaches that we have used to leverage knowledge from elsewhere. So the methods of knowledge leverage include leveraging through data, through representations, and models. I will start by describing our work in data leverage through data augmentation, which is used for dysarthric speech as well as for older adult speech, and the individuals may have cognitive impairment. So to start off, I'm going to talk about data augmentation for dysarthric speech recognition. Data augmentation has become widely used in the speech community, but this work is a study of data augmentation in this novel context of disordered speech. And this paper was published in Interspeech 2020, which is primarily authored by Meng Zhegeng, who is a PhD advisee of Professor Shinying Liu, my colleague. And this paper presents a systematic investigation of data augmentation for dysarthric speech recognition. Now, it is very difficult to collect a large amount of dysarthric speech recognition, mainly because of the condition of the speaker. Now, actually, please let me play for you an example of dysarthric speech in English. Okay, and here is one in Cantonese. So you can see that there's oftentimes some distortions in articulation, and you can also maybe notice that sometimes it's very hard for them to control their articulatory movements, including the speed of the speaking rate. Now, we actually have investigated 3 types of perturbations: vocal tract length perturbation, tempo perturbation, and speed perturbation. And 2 methods have been used, which include perturbing healthy speech to become disorder-like speech, but also perturbing existing disorder speech to become further modified disorder speech. The acoustic model is a hybrid D and HMM model, and multitask learning is used. And you can see that it's learning based on tight triphone state and also monophone alignments as the labels. And to better model the large variability among the dysarthric speakers, learning hidden unit contributions, L-hook speaker adaptive training is further applied. And this speaker-dependent L-hook layer is inserted after the ReLU of the first layer. Now, evaluation is conducted using the UA speech corpus, which is an isolated word recognition task. You can see that this data is very precious, and it is in rather small amounts, coming from 13 healthy speakers and 16 dysarthric speakers. And after silent stripping, we have about 30 hours of training, and speed perturbation was found to work well for improving speech recognition performance, reducing the word error rate. And you can see that when we perform data augmentation from 30 hours to 130 hours, that brings down the word error rate from 31.5% to 28.7% and begins to converge. Now, the final system that we use is further enhanced with L-Hook speaker adaptive training and compared with recent system, including our own published system in 2018, and also the system by Xiong et al. In 2019, you can see that the latest word error rate of 26.4% should be the best results reported for UA speech so far. Now, this data augmentation strategy is then applied to older adult speech recognition. This is a paper by Ziye, who is also a PhD advisee under Professor Xunying Liu. And this paper was presented at ICAST 2021 just a few days ago. This project uses the Dementia Bank PICT corpus for automatic speech recognition development. This is the largest publicly available English data set for recordings that involves an investigator and the participant who is an older adult. And it involves participants who may be healthy speakers or who may have neurocognitive disorders, especially Alzheimer's disease. So the conditions may be mild or major. Now, Dementia Bank actually had 4 tasks, but in InterSpeech 2020, there was the Address Challenge, Alzheimer's dementia recognition through spontaneous speech, that extracted one of the tasks known as the cookie theft picture description task. And here I show you the picture. And here is an audio from a healthy control speaker.
Well, there's a mother standing there washing the dishes, and the sink is overspilling. And the window's open, and outside the window there's a walk, a curved walk with a garden.
And here is another speaker who has Alzheimer's disease.
The little boy is up on this thing here, and he's up trying to get something out of the garden selection, I think it is.
So in this project, what we did was to follow the partitioning in the address challenge and prevent data leakage and ensure fair comparison with other systems. And the objective is to detect whether the participant has Alzheimer's disease based on their speech. So our student, Ziye, she began with resegmentation and silence removal, which led to only about 16 hours of speech remaining, which is, again, very low resource. And with data augmentation, we enlarged the training set to about 60 hours of speech for training. And you can see that through this process, the word error rate was brought down from about 45% to 37%. Now, further following up with cross-domain adaptation using about 1,000 hours of speech from library speech corpus, adapting to Dementia Bank, and together with the L-Hook speaker adaptation, followed by the transformer language model, we were able to obtain a word error rate of 33.2%. Now, this is another paper which was also presented at ICAST 2021, and this paper is primarily authored by Jinchao Li, who is my PhD advisee. And Jinchao uses this the automatic speech recognition derived transcripts and compare them with manual transcripts for Alzheimer's disease detection. So you can see that we have the manual transcripts with basically 0 word error rate. And then we have 2 systems, the baseline system at about 45% word error rate, and the best system that we have so far, 33.2% error rate. And Jinchao found that when we use BERT features So this is bidirectional encoder representations from transformers together with SVMs for AD detection. And note that the BERT-based tokenizer is pre-trained on the book corpus, which contained 74 million sentences. And it encodes the ASR transcripts or the manual transcripts as bidirectional contextual features, which are then used for AD detection. Now, while most of the previous systems use manual transcripts, this work is among the first that demonstrates that at word error rate of 33%, Alzheimer's disease detection using the BERT features is comparable with that of manual transcription. This work is actually part of a cross-university collaboration in Hong Kong and funded by the RGC theme-based research scheme. And our partners, in addition to Chinese University, include my colleague, Professor Man Wai Mak from Polytechnic University of Hong Kong, and also Professor Brian Mak from Hong Kong University of Science and Technology. Now I will move on to approaches that uses knowledge leverage through representations. And I will cover two examples. First being adversarially trained speaker representation, followed by self-supervised pre-trained representation. Now, first is adversarially trained speaker representation, and this is for speaker diarization on cognitive assessment speech recordings. This work was actually published in an ISCSLP 2021 paper, primarily authored by Dr. Sean Zhu, a postdoc at Poly University, and advised by Professor Man Wai Mak. It tackles the problem of speaker diarization and uses a corpus of Cantonese MoCA recordings. MoCA stands for Montreal Cognitive Assessment. And again, it's a set of recordings which involves a dialogue between the clinician, the investigator, and the participant. And speaker diarization is the task of figuring out who spoke when, and it is the first step in analyzing the speech recordings to focus on the participant's speech. Here, we see that the speech parts of the audio are extracted as short segments, and these segments are embedded into a space that represents the speaker's characteristics. The segment embeddings are then clustered and are used for diarization. Now, a key problem is how to embed the speech segments such that different speakers can be embedded into different positions in the embedding space, regardless of their speech content. And X vectors based on time delay neural networks are often used. Now, Sean used the Cantonese MoCA recordings that we have collected, which include dialogues from 67 participants. This corpus is growing, and the participants are aged 72 or above. Now, because there is basically no Cantonese data available yet for training, so we use English data for training. The English data comes from the NIST SRE corpus and also the switchboard corpus. Now, let me first play for you a Cantonese MoCA recording.
爸爸頭先咪叫你記住嗰3樣嘢嘅，邊3樣嘢啊？蘋果、報紙、火車。好。呢樣咩啊，爸爸？鉛筆。咁呢個咧？手錶。好，嗱，爸爸麻煩你跟我講句説話嚇。姨丈買魚腸。姨丈買魚腸。好。
So you can see then that while our test set, the target evaluation set basically involves elderly participants, the training data has the age profile illustrated here. So most of the speakers come from the young group. And this age mismatch between the training set and the test set will affect diarization performance. So adversarial training is applied to reduce the age variability in the speaker embeddings. This age classifier is added here, and the gradient reversal is done during backpropagation so that the encoder can learn to can learn embeddings that are speaker discriminative while the age information is reduced. Now, if we look at the diarization error rate across 3 systems, we have systems 1, 2, and 3, and that uses different training data. You can see that system 1 has the most training data, but the data does not have any age information, so we can only use the traditional speaker embedding, and we cannot apply age invariant speaker embedding. The diarization error rate was at 6%. Now, systems 2 and 3 had training data with age information, so both are able to apply age invariant speaker embedding. And if you look at system 2, you can see that the age invariant speaker embedding actually achieves a diarization error rate, which is much, much lower than the traditional speaker embedding. And similar trends are found, and a similar trend is found for system 3, which has slightly more training data. And we can see how age invariant speaker embedding can help us tackle this lack of older adult speech data. In fact, even with such small amount of data, with age invariant embedding, systems 2 and 3 are performing even better than system 1. Now I move on to the second example of representation leverage, which is on self-supervised pre-trained representation. And here we look at the task of Chinese accented English speech recognition. And this kind of Chinese accented English speech is explored under the context of mispronunciation detection and diagnosis for computer-aided pronunciation training. We have been working in this area for some years, and our graduates, Dr. Kun Lee and Dr. Li Fa-Sun, they have established a company known as SpeechX that deploys a pronunciation training service on WeChat, and this service has over 1 million user logins per day. So let me play for you a demonstration of this service.
Sit.
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 Sit. I would like a piece of steak.
Steak.
Steak. Prosody.
Prosody.
Prosody. Prosody.
Okay, so to illustrate the difficulty of accented speech, Chinese accented speech, here is an example audio.
The lost wind and the sun were disputing which was the stronger when Trevor came along wrapped in a warm cloak.
We input this audio into a couple of state-of-the-art ASR systems, and you can see that from the outputs of these recognizers, you can see that in general, the accent does not agree with them too well because their training data probably do not have good coverage of Chinese accent. And a staff member in our team, Wai Kim Leung, in ICAST 2019, he published a paper where we used the sequence-to-sequence approach, which is trained on 24 hours of speech from this corpus, Chinese University Chinese Learners of English corpus, CU Chloe. And also, we trained on a 5 hours of data from the TIMID corpus. And this serves as our reference system. Now, recently, we have tried to use self-supervised pre-trained speech representation, which is known as Wave2Vec, which comes from Facebook AI. And this is work done by my PhD advisee, Minlin Wu, and his paper has just been accepted at Interspeech this year. So Wave2Vec has been trained on 960 hours of library speech data, unlabeled raw audio through self-supervised learning. And this is used in the downstream task of mispronunciation detection and diagnosis. And it is trained further using 24 hours of accented speech data from CU Chloe. Now, you can see, based on the comparison on the evaluation, 7 hours of Chloe test set, you can see that the evaluation is illustrated here. Let me just quickly explain. So we look at the human transcribed phones of the accented speech, and we compare it with the canonical pronunciation to determine correct pronunciations versus incorrect pronunciations. And for the pronunciations that are deemed correct by the human, we can compare with the output of the system to determine whether there was true acceptance versus false rejection. And for the pronunciations deemed incorrect by the human, we can refer to the system's output to classify false acceptance versus true rejection. Now, for true rejection cases, we can further look at the phone recognition output and compare it with the human transcribed phone to determine whether there was correct mispronunciation diagnosis versus incorrect diagnosis. Now, in terms of phone error rate, you can see that our reference system had a 12% phone error rate, but Wave2Vec gave about 6%. So it's a significant improvement. It also significantly lowers the false rejection rate. The false acceptance rate between the two approaches are about the same at 20%. And the diagnosis error rate of the Wave2Vec system was also significantly improved by about 48%. So you can see that the pre-trained model, the representation of Wave2Vec, enables us to leverage knowledge for accented speech recognition, which brings a big boon to the overall mispronunciation detection and diagnosis performance. Now I'm going to talk about model leverage, and I will cover 3 examples: meta-learned models, knowledge distillation with multitask learning, and knowledge incorporation. Starting with meta-learned models. Here, we're looking at dysarthric speech recognition. Now, meta-learning aims to teach a model how to learn various tasks so that it can solve new tasks with few samples. And due to the sparsity of dysarthric speech data, it is necessary to start with a base model that is generally trained with sizable normal speech data, and then we want to adapt them to individual dysarthric speakers. However, because of the mismatched statistic distributions between normal and dysarthric speakers, it restricts the generalization ability of the base model, and speaker adaptation may be difficult. This paper by my PhD advisee, Di-Sung Wang, which was published in ISCSLP 2021, explored the use of base model reinitialization, where meta-learning is used based on dysarthric data, so that the reinitialized model, you can see in this reinitialized model here, it can fast adapt to unseen dysarthric speakers with improved performance. Now, Di-Sung actually experimented with 2 meta-learning algorithms, MAML and Reptile. In MAML, the adaptation to each dysarthric speaker is treated as a task. So you can see each of this is a task. And the meta model, theta star, is initialized with a base model, which is trained on 960 hours of library speech. And meta updating involves the inner loop optimization followed by the outer loop optimization. Now, inner loop optimization adapts to each speaker using the training data that is sampled from the adaptation data and implementing J-gradient descents. Then in the outer loop, these individually adapted models theta I are then used together to update the meta model theta star using validation data, which is also sampled from the adaptation data. In the Reptile algorithm, the inner loop optimization is similar to MAML. The outer loop optimization does not need validation data. Instead, the meta model theta star is updated by averaging the gradients contributed by each adaptive speaker model theta I. Hence, if Reptile adapts with a single step, J being equal to 1, it is the same as joint training. This explicit integration of speaker adaptation into the reinitialization process steers the model to be optimized for generalization. And this reinitialized model acquires speech knowledge across dysarthric speakers for fast adaptation to unseen dysarthric speakers with improved performance. So in our experiments, we compare different approaches. First, having the base model adapted with 900, this is the base model, trained with 960 hours of normal speech data and adapted by each with the data from each dysarthric speaker, which is under 2 hours. Then we also used meta-learned reinitialization involving joint training, mammal and reptile algorithms. And here we pull the adaptation data across dysarthric speakers, except for the target at any given time. And then we adapt to each individual speaker for fine-tuning. You can see from these learning curves here that the meta-learned models, the yellow and the green curves, the meta-learned based models, reinitialized base models, it can rapidly lower the word error rate in just the first few adaptation epochs and attains the lowest word error rate amongst the various approaches. So it validates the powerful generalization ability to unseen dysarthric speakers, especially under a low data resource scenario. Now I'll move on to the knowledge distillation and multitask learning example. Here, we're looking at the process of dysarthric speech reconstruction. This is the process where we input dysarthric speech features and reconstruction will output normal speech features by reconstructing the articulation as well as the speaker identity. And for now, we will focus on articulation. This problem was first studied by Kane et al. In 2007, where GMMs that were trained on parallel data was used. But as you know well by now, there is a scarcity of dysarthric speech data. And furthermore, parallel data of dysarthric and normal speech data are generally missing. So this is a problem. And in fact, this work was published in ICAST 2020. So what Di-Sung did, as written in that paper, was to explore and compare two approaches. The first one is probably comes straight to mind as a possible approach for speech reconstruction. This is the dysarthric speech passing through ASR, getting the text, and then go using TTS, text-to-speech synthesis, to get the reconstructed speech. Now, the problem here is that especially in cases where there might be severity in the speech disorder, ASR may have errors, in which case, if the text is misrecognized, is the misrecognized output, then the TTS will be synthesizing a different and altered content. So therefore, Di-Sung's paper proposes that we need a speech encoder that can extract content and pronunciation knowledge from the input dysarthric speech into a representation that can be used by the generator to generate reconstructed normal speech that restores the content, but also that bears some resemblance with the original dysarthric speech pronunciations. So as you can see from this diagram here, this approach should benefit greatly with parallel normal and dysarthric speech data, but this is generally lacking. So using the UA speech corpus, we have less than 2 hours of dysarthric speech and about 30 hours of normal speech. So to train the speech encoder, Di-Sung proposed to use a knowledge distillation approach to transfer knowledge from elsewhere. In general, knowledge distillation aims to improve a student network by borrowing knowledge from a powerful teacher network. Now, if we consider a sequence-to-sequence text-to-speech synthesis engine, it can generate speech from characters, character input. So this text encoder can actually extract knowledge in the character embeddings that can be used by the generator to generate normal speech. So Di-Sung uses this text encoder as the teacher to guide the speech encoder here. This becomes a cross-modal knowledge distillation problem because it involves the modalities of text and speech. And cross-modal knowledge distillation is trained on the transcribed speech from UA speech corpus, which gives us both text and audio. And this speech encoder is then guided to imitate the text encoder to extract spectral embeddings from the input speech. And this imitation is achieved by the use of the mean square error loss and the adversarial loss. Now, the mean square error loss aims to constrain the output, constrain it through point-by-point calculation of the L2 norm between the character and the spectral embeddings. And so it's a local constraint. And a more global constraint is applied using the adversarial loss, which reduces the statistical distribution difference between the character and the spectral embeddings. And in addition, DSong uses multitask learning to further enhance the speech encoder using this auxiliary task, which uses an auxiliary loss. So in fact, multitask learning is where we learn from multiple related tasks in parallel to leverage domain-specific information for better generalization in performance. So this multitask learning paradigm is used to tackle data sparsity problems where the information from the related tasks can be shared. And here, in training the speech encoder, we leverage the sequence-to-sequence approach using the CTC for ASR to steer the spectral embeddings to capture textual or character information so that the ASR loss contains both the cross-entropy loss and the CTC loss in character prediction. So now what we have here is a speech encoder, and it is trained with knowledge distillation as well as multitask learning. So it can take in unseen dysophoric speech. Let me just show you. So it was here before, so we can move it over here. All right, so it can take in new dysophoric speech data to generate spectral embeddings, and then we move the generator from the TTS system over to have now an end-to-end speech reconstruction system. So here we are able then to transform dysophoric speech to normal speech. So you may then be interested to know what would be the comparison between these two approaches, the ASR-TTS approach and this new approach of knowledge distillation with multitask learning. So here, what we have done is to compare between the two approaches using the reconstructed speech based on naturalness, mean opinion score on naturalness, and also human speech recognition accuracy. So you can see that if you focus on the shades, the medium and dark shades, you can see that in general, the knowledge distillation multitask learning approach performs better than the ASR-TTS approach. With the exception of here, we have cases of a moderately severe and severe speakers where the baseline approach, ASR-TTS, has a higher mean opinion score. But in fact, in these more serious cases, ASR is prone to misrecognition, and so the TTS actually sounds natural, but the content may have been changed. So to illustrate this point, let me first play for you one of the moderately severe dysophoric speaker. Here it is. This is the original recording where he is trying to say the word escape. Okay, and here is the ASR-TTS output.
Escape.
And this is the knowledge distillation MTL output.
Escape.
And if we perform restoration of speaker identity as well, it sounds like this.
Escape.
Okay, here's another example of the word feather. This is the original recording.
Feather.
And this is, oops, sorry, my mouse is not doing very well. And then this is the ASR-TTS output.
7.
So the content has been changed to another word. This is the KDMTL output.
Feather.
And this is if speaker identity is restored as well.
Feather.
Okay, so you can see that in fact, the advantage of knowledge distillation and multitask learning is that it can be more effective in preserving both the content, I should say the content. In fact, preservation of the speaker identity is a paper that is forthcoming. Now I will move on to the third example of model leverage, which is using knowledge incorporation, which is applied to code switch speech. So as someone who is born and raised in Hong Kong, which is a place with two official languages, English and Chinese, code switching is very much part of my identity. Oops. Okay, so code switching refers to language alterations in speaking and writing. And in Hong Kong, we oftentimes code switch between Chinese and English, like this one, 为你播放 Beatles in my life, which can be translated as playing Beatles in my life for you. And code switch TTS aims to synthesize with natural and consistent voice across languages. However, the challenge of code switch TTS is that there's oftentimes very limited multilingual or code switch data from the same speaker. It's hard to find a speaker who has very high proficiency in multiple languages and be able to record for both languages from the same speaker. So oftentimes researchers use a mix of monolingual data, but this will imply that the code switch language alternations would have been never accessed during training, and also that speaker and language characteristics are often entangled in monolingual corpora. This work is part of my PhD advisee, Yuewen's Hao's PhD work, and this part is conducted during her internship at Tencent AI Lab. So what we need is a speaker-independent phonetic representation for multiple languages in a compact feature space. And this representation must be able to disentangle between language and speaker characteristics. So our proposed approach is to use phonetic posterograms. This is a representation, and it actually is a time versus class matrix that represent posterior probabilities of each phonetic class and at each specific time frame of an utterance. So it actually carries a lot of phonetic class knowledge. And it can be extracted from ASR, and it is deemed speaker and language independent, which has been used previously in our work in voice conversion. You can actually refer to our previous papers, and we have found that PPGs are very effective in voice conversion. And in fact, more recent work by Yi Zhou et al. Used bilingual PPGs that are stacked, that are derived from two monolingual PPGs stacked together, each being obtained from a speaker-independent ASR engine, and it actually benefits cross-lingual voice conversion. So first, we reference Google's work on voice cloning, cross-lingual voice cloning. And this system is trained on sizable data, as you can see here. And therefore, you can actually select the different source speaker and listen to their code switch synthetic outputs. This is from the English speaker.
使用左侧车道向3后 Z 方向行驶。
And this is from the Chinese speaker.
使用左侧车道向3后 Z 方向行驶。
However, since we do not have code switch data available, so Yuewen decided to pick two different corpora, about 10 hours each, English and Chinese, 10 hours each, and we have this data replicating the same approach using this data. And here I play for you the synthetic outputs coming from the English speaker.
使用左侧车道向3后 Z 方向行驶。
And this is from the Chinese speaker.
使用左侧车道向闪后线方向行驶。
So this actually has a rather distinctive decline in terms of the quality. So instead, we propose to use bilingual PPGs. So we first extract these bilingual PPGs and stack them together. And this is the middle part where we put the reference system down here. But instead of using MEL spectrograms, we now incorporate bilingual PPGs. Okay, and then because we are able to use bilingual PPGs, which has which is speaker independent and language independent, we can actually take out the adversarial training that is explicit in the previous approach, okay, that performs speaker and language disentanglement. And then voice and voice flag information and also log F0 information is added in to enhance the prosody. And then this is augmented with the speaker embedding and used to generate the mouse spectrogram and generate the wave RNN, the wave using wave RNN. Now, in the testing phase, basically you can see that we use the phoneme sequence and we generate the bilingual PPGs together with the other prosodic information, voice and voice flags, and the log F0. And this can be augmented by the speaker embedding, so you can control which speaker, source speaker that you want to use. And this is then used to generate the mouse spectrograms and then further generate the wave using wave RNN. So now I want to play for you some of the outputs from this code switch text-to-speech synthesis using bilingual PPGs. And so our reference system is text to mouse spectrograms, and our proposed system is text going to bilingual PPGs to mouse spectrograms. And you can see that the mean opinion score on intelligibility here, the orange bars are higher, so the bilingual PPG seems to have an advantage. This is based on 20 hours of training data. And let me just play for you the source Mandarin speaker recording. This is the original recording from the source Mandarin speaker.
入夏以来，雨水充沛，利于作物生长发育。
And this is from the English speaker.
He had a big chimpanzee that was a winner.
Now, here is the recording of this code switch input using the reference system.
为你播放 B 组件也难来自。
This is coming from the bilingual PPG system. Oops.
为你播放 Beatles Day My Life.
All right. And so this is synthesis based on the Mandarin speaker. Now we can also synthesize using the English speaker speech. And this is another code switch text. And this is using the English speaker speech reference system, reference approach, which is a text to mouse spectrogram approach.
是Wolf去到San Jose for Sansos.
And this is the bilingual PPG approach. Okay, so you can see that by incorporating bilingual PPGs, we're able to have this approach survive on only 20 hours of training data. And just for fun, we're also able to do code switch wrapping synthesis. This is work done with our graduate, Dr. Shi Kang, who's a graduate from our team, and also conducted by Yuewen Cao during her internship at Tencent AI Lab. So together with a wave to lip model, we're able to do code switch wrapping synthesis.
我们开心就拍手，开心就喝酒，开心就把你身边伏特加都带走。I say one shot, baby, two shots, baby， 从地下室爬到上来。
Okay, so now going to the conclusions and future work. So in this talk, we had brought forth the point that while speech and language technologies are permeating our daily lives, technological inequity exists for many kinds of users and usage contexts. And the key challenge is due to data scarcity and sparsity, which is aggravated by the high data variability. And in this talk, I've presented for you a spectrum of knowledge transfer techniques that apply data, representation, and model leverage to handle this low data resource challenge. And we have demonstrated the effectiveness in different types of speech and tasks. So the different types of speech include accented speech, code switch speech, dysalphic speech, speech of older adults who may have cognitive impairment. And the tasks include recognition, diarization, mispronunciation detection and diagnosis, as well as synthesis. Now, these techniques that I have presented are actually quite extensible and widely used in other tasks, such as emotive speech synthesis and any-to-many voice conversion. So emotive speech synthesis, there's infinite ways of expressing an emotion. So basically data is always scarce and insufficient. And any to many means any speaker, from any speaker to many speakers, voice conversion. And so therefore, we can't have that kind of labeled training data from any speaker to many speaker. And so these approaches can also be effective. We have a few papers coming out in the IEEE Transactions, TSLP this year, on these topics, emotive speech synthesis and any to many voice conversion. Now, looking into the future, we must strive to develop speech and language technologies that can gracefully adapt and accommodate a diversity of users and usage contexts around the world. And of course, we're mindful that among the 7,000 some languages in the world, a large proportion of these languages suffer from data scarcity and data sparsity, and many do not even have a written form. And these endangered languages are disappearing, so we must try our best to preserve them. And our long-term goal is to advance technological equity towards universal usability of speech and language technologies. So with that, I thank you very much for your kind attention. Thank you.
Helen, thank you very much for a very, very interesting talk. It was a pleasure to listen to you and see what you've done with all your students and colleagues. We have just a very short time for 1 or 2 questions if someone have a question. They can write on the chat. Okay. Meanwhile, I have a question to you. When you spoke about diarization, you show that you have a representation that is age-independent representation. I would assume that a representation which can better distinguish between female and male, young and old, will help the diarization, but you show it vice versa, that you want to be age-independent. How can you explain that it improves the diarization?
Oh, thank you very much, Isha. So ideally, we, of course, would like to be able to, assuming, for example, if the investigator is young, and so the clinician is generally young, and the participant is old, then if we have that kind of training data for diarization, we should definitely try our best to leverage the discrimination between speakers by age or by gender or whatever knowledge you have. But as a start, as I was not clear enough, as a start, we have Cantonese MoCA data that is recorded in our medical school. We don't have enough training. In fact, we don't have any training data for it because we only have about 67 participants. It's growing. So we can only use English data from NIST SRE and also from Switchboard. And in Switchboard and NIST, you can see that there are very, very few senior speakers who are age 60 or above. And so basically, very few. So therefore, our training data lacks older adult speech, lacks that information. So therefore, whatever embeddings that we use coming from the training data are mostly from young speakers. And those kinds of embeddings, the young speakers' embeddings, they're predominant. So they will not apply so well on our recordings where we will have an investigator and a participant. So we don't want the age information to overwhelm. To overwhelm. So we want some representation that is speaker discriminative, but not age discriminative, because our training data is mismatched with our testing data.
Okay. Okay. Thank you very much for the answer, and thank you very much for the talk. And it was very, very interesting. Now we will move to our next speaker. Thank you very much. And Now we proceed to the talk of Or Niger. Or is a PhD student at Ariel University. His talk title is Exploiting BERT for Cross-Lingual Vectors to Speaker Change Detection. Please, Or, you can come here, please.
Hi.
Thank you very much for joining to the conference.
Thank you.
The stage is yours.
Thanks. Hi, everyone. My name is Or. I'm supervised to my PhD by doctors Amit Dvir and Chen Hajjaj, and Itzik is also co-advising me in the last year. And today I'm going to show how to exploit this lingual model for the creation of cross-lingual vectors for the problem of speaker change detection. So as already known, the speaker change detection is the task of segmenting an input audio recording by the speaker interchanges, which is quite useful for applications like speaker diarization, automatic vocal transcription, and so on. Previous works have already shown that textual content appears to be very useful for solving problems like speaker change detection or diarization. And in this work, we are going to show how to, we're going to focus on the audio segmentation process, but from the multilingual aspect. For instance, we can see in the figure in this slide, from the right side of the figure, we can see the word article in English and its translation to German article. It's a word embedding space for the both of languages, English and German. And we can see that they are quite written by the same manner, whereas words like money and geld are placed in the top left corner of the graph. Even though they are not written by the same manner, they share the same meaning. So let me first present BERT, which is a language model presented by Google. It's a synonym for bidirectional encoder representations from transformer. Well, a transformer technically is a model that adopts the idea of attention mechanism, which basically measures the influence of different parts of input data over the outputs. For instance, in the task like language translation, if we want to translate a sentence from English to Hebrew, so not always the word order or the number of words remains the same when we move towards the Hebrew sentence. For instance, if we take the sentence when the ladies came, so in English, we can represent it in one single word in Hebrew. So the goal of the attention mechanism is to learn how to map the relations between the words in the English sentence over the output in one single word in the Hebrew language. So BERT was pre-trained from a dataset of book corpus that contains 800 million words, and also over the English Wikipedia dataset that contains 2.5 billion words. In this work, we use a model that is called the agnostic BERT. It's a multilingual version of the well-known BERT model. It can produce word and sentence embeddings over more than 100 languages, including English and Hebrew. And it's already shown in the paper that presented the agnostic BERT how to improve several NLP tasks like named entity recognition, sentiment analysis, Q&A engine, and so on, for almost 84% of accuracy in average. So basically, our work suggests a framework to tackle the SCD problem, but from a hybrid standpoint that combines multilingual data sets. So basically, our dataset is audio recordings that we translate or transform into continuous text files, usually using a speech-to-text engine, and in order to create a shared word embedding, as well as a speech embedding module that is computing through D vectors. Finally, we add another metadata features that are extracted from the text and speech signals, and then we train a hybrid neural network in order to solve the change detection problem. So as for the speech signal, as I said, we use D vectors trained by a speech embedding neural network that we already pre-trained over some data set. We'll show it later. And the input of the speech embedding neural network is speech utterances of different lengths. As for the text signal, we encode each word or sub-sentence. We'll see how using a 768-dimensional vector, using the encoding method of agnostic BERT, as well as the metadata features like pronunciation duration of each word, the speech rate that we try to model, and distance metrics. So first, we iterate over the conversation where the audio that are translated from the speech-to-text engine using the sliding window method. Each sliding window contains 6 words, where the target label is to detect whether there is a speaker interchange between the third and the fourth words in a sliding window. So we can see, for instance, SI or SI plus 6, which are the green sliding windows on the figure. And we can see that there was no speaker interchange in these sliding windows. Whereas on the red sliding window, which is SI plus 6, we can see that there is a speaker interchange between the third and the fourth words, between the speaker identities. Just to be clear, if we would take the sliding window SI plus 5, that contains 4 words of the first speaker and the last 2 words of another speaker, we won't consider it as a speaker interchange. So as for the text signal, we hold 1,536 features, and by this manner we represent each sliding window from the textual aspect. So we use agnostic BERT to encode the first 3 words of each sliding window, and we get a vectorial representation of 768 features. And so we do for the last 3 words in each sliding window, and we get an additional 768 features. As for the speech signal, we represent each sliding window with 512 features, where 256 are serving for the D vector that takes to pronounce the first 3 words in each sliding window, and another 256 for the last 3 words in each sliding window, which are the fourth word and the 6th one. I know it's a bit different from the regular computation in the speech community, but as we already own the dataset with the starting and ending time of each word, we can compute the D vectors from this representation. Finally, we compute 14 additional metadata features that in order to represent each sliding window, where 6 of them are each word's duration, another 6 tries to model the speech rate of any speaker by divide any word duration by its number of characters. And an additional 2 features, one of them is for the time elapsed between the third word and the fourth word in any sliding window, which might imply about some speaker interchange if there is a big difference between the ending of the third word and the starting of the fourth word. And finally, we had the Euclidean distance between the 2 speech embedding vectors of any sliding window, and then we can train our model by concatenate the component of speech, text, and metadata through hidden layers of a fully connected neural network. We denote this model by TSMD SED, which means text, speech, and metadata speaker change detection. So before we dig into the experimental evaluation, let me first present the dataset on which we used in this experiment. So for the English language, we used the well-known ICSI dataset. It contains 70 hours of meeting recordings, involve 8 different speakers, and contains in each conversation contains between 2 and 6 different participants. Whereas the Hebrew dataset is a commercial one that serves only for academic purposes. It belongs to IFAT group. It contains almost 1,700 audio recordings with the textual transcription, and involve 1,240 different speakers, where there are between 2 and 5 participants in each audio. So eventually, after training several versions of the TSMD model, let me please explain each one of them. So first, we trained TSMD version of over the datasets in English and Hebrew. We call this model the multilingual DSMD, which is represented by the first line of this table. And then we trained separately over the Hebrew datasets and the English datasets the TSMD model, and we can see these models in entries 2 and 3 in the next table. So we can clearly see that there is a bit degradation between the performances of the single language-based TSMD model against the multilingual version of TSMD. We strongly believe that this gap is caused since English is a Semitic language and Hebrew is a Semitic language and English is a West Germanic one, and they are quite distant languages, so it's a bit hard to represent them perfectly in one single model. But in order to assess to prove that textual content indeed improves the solution of change detection systems. So we trained the TSMD without the textual component, only over the speech signal and the metadata. So we can see in the entries 4 and 5 on this table that the results are much lower than even if we train the SMD model separately over one language. So even though the results seem quite promising, yet there is a gap when we want to add or remove one or more languages to our model. Yet we can easily adopt our framework using the encoding method of agnostic BERT that can embed word and sentences in more than 100 languages, which cover a respectable percentage of the spoken languages around the world. And from the technical aspect, our additional future work direction is first to check the SMD model, which is without the text at all, by adding a voice activity detection engine. Then we plan to cope with overlapping speech and data sets in different languages than Hebrew and English. And in addition, we will try to use different deep learning architectures, as well as using alternate acoustic features than D vectors, like X vectors. So thank you very much.
Thank you very much, Oro, for a very interesting lecture.
Thank you.
I have one question to you. The agnostic BERT is using 109 languages. So it's agnostic only to these languages.
Right.
If you want to add 1 or 2 new languages, is it possible?
Yes, you have to fine-tune agnostic BERT from you with your additional data set, and by this way you can add a new language to your model.
And then we can use it?
Yeah, clearly.
Okay, thank you very much to you.
Thank you.
Okay, and now we proceed to our second part, and Professor Vera Aronson will chair this session. Okay.
Thank you, Itzik.
Bye-bye.
Yeah. So we proceed to our second session, which is the healthcare session, speech processing for healthcare. Now this has been performed in the last 6 years, a separate conference. And actually the last one was in January 20th, 2020. And little did we dream that a month later we'll be plunged into COVID research. And although we could have easily filled this session with only COVID research, this conference, we are going to focus on symptoms that can be related to, but pertain not only to COVID, namely respiratory symptoms, throat, and vocal cords. So I'm delighted to invite our keynote speaker, Professor Marcelo Finger from the University of Sao Paulo, Brazil, who leads the NLP group in the USP IBM Center for Artificial Intelligence. And he will present his group's work on respiratory disorders analysis from speech. Hello, Marcelo. Good morning, and thank you for joining us.
Hello. Hello. Thank you very much, Verit. Toda rabah for your invitation. I'm very glad to be here. Today I'll talk about our project, which is called the Project Spira. Spira is a acronym in Portuguese. It's the System for Precocious Detection of Respiratory Insufficiency via Audio. So why do we want to detect respiratory insufficiency? Well, this was a proposed response for the initial spread of COVID-19 pandemic in Brazil. The hospitals were overloaded with people, and we wanted to help trying patient triage, like the selection of patients by voice. We would like to separate the hard cases, the serious cases, from the simple cases, people that should and should not go to the hospital. So we tackled the main symptom, which is a silent hypoxia. Silent hypoxia means low blood oxygenation levels, but without any other manifestation. So it's silent. The person doesn't feel that he or she is with the lack of oxygen. And in COVID, this is what was a very serious symptom, and we wanted to detect that, to know if it was possible to detect that via audio remotely from home or any place through speech, voice and speech. So this silent hypoxia can also happen in cases of other diseases like influenza, heart disease, lung problems, sleep disorders, anxiety attacks, etc. So, and this idea was developed together by me and two colleagues, Esther Sabino and Ana Sarah Levine Schafferman, at the medical school at University of São Paulo, Brazil. So, so the project kicked off well. We started with where we were accepted by the ethics committee. We found the funding from the São Paulo funding agency. We associated with the IBM FAPESP Center for Artificial Intelligence, in which I had the natural language processing challenge of research. And then we started the project. Just for you to have an idea of the size of Brazil. So this study is based in the city of São Paulo, which has 11 million. The São Paulo metropolitan area has more than twice as much, so it's 21 million people. And the whole state of São Paulo, which is the São Paulo metropolitan area, and the interior areas and the other areas of the state, reaches 45 million amount. So this is about 1/4 of, or a little bit less than the whole of Brazil population, which is 2011 million, according to the latest estimation. So, and the COVID numbers, as of last Friday, we had, in the city of São Paulo, we had 800,000 cases with 31.5 deaths. The São Paulo metropolitan area had twice this number, and the state has 4 times this number. In Brazil, we already have, unfortunately, 17.2 million cases. We are reaching in a few days, regrettably, the mark of 500,000 deaths by COVID. So yeah, so it's 482,000 deaths last Friday. So so this is the why we investing in that, the size of the project and the project structure. We decided to study speech as a biomarker. So, and we collected data in the wild, I mean, in the hospital with all the noises, everything, no special room, no special recording equipment, cell phones were used. We had 2 investigative fronts in our project. One dealing with the small data, like looking at the sign of the data, doing traditional research on phonetics and audiological and speech therapy, etc., on audio samples, and big data project, which is actually trying to make a big data program using neural networks with automated learning to detect respiratory insufficiency. So the research question we were addressing is it possible to detect respiratory insufficiency from audio recordings? Just because we thought we could, that doesn't mean that we can. So like just a bunch of Brazilian nuts says, well, you want to detect respiratory insufficiency. Can we? That's the whole point of this project. And so we constructed 2.5 data sets, actually. One data set from people at the hospital here on the left, you can see someone collecting from a patient her voice using only a cell phone. And we also had a web-based application for cell phones and browsers, etc., to collect the voice from healthy people. So we had almost 600 samples from the voice collections from patients from COVID wards in the university hospitals, and the university hospital is one of the largest in Latin America. So we had a big pool of people to collect from. We had more than 6,000 voice donations from people at home. They just came up voluntarily and donated their voice. And in the very beginning, we noticed that the two collection environments were very different. Like the hospital, a COVID ward is one of the noisiest places in the world, full of noises of machines, beeps, people moaning, coughing, etc. So we started collecting also the noise from the room with no voice, nothing, just the noise from the room. And this was important and used in our study to avoid biases. Okay, so we had this data set, and then at the time, it was the first wave of the pandemic. We thought we would have nurses and doctors available, but we were wrong. We had to resource to medical students to do the collection for us. We had no special recording equipment. We used cell phones in COVID wards, and the COVID wards were in two of public hospitals, the University Hospital and the Clinics Hospital, which is the largest in Latin America, and also one private hospital took part in that data collection phase. So once with the first wave decreased, this data collection stopped, and then we had the problem of how to process the data. We had the problem of background bias. This is the signal. You can see it has a lot of noise. We started to filter that noise, but then we had we were afraid that we were if we delete the noise, aren't we possibly also deleting the important information that can detect COVID for us? So we were afraid of throwing out the baby together with the water. So we decided not to filter. So we in the dilemma noise reduction or noise insertion, we actually decided instead of removing the noise from the COVID data, we decided to add the noise to the data. In the beginning, we thought we needed only to add data to the noise, sorry, to the control page, the healthy people. But in the end, we decided we had the better results if we add noise to both kinds of signals. So in the end, here is the amount of noise samples that we need. And we found out that a noise sample is a packet of noise. We decided if we add 3 noise samples, both to the patient data and to the control data, and then we use a balanced COVID data set because we had much more control data, so we could balance it with the gender and age to be more or less the same as the people in the hospitals with the patients. And we did some transformation in the signal. We got better results when instead of using the sound noise, we transformed it with the sampling to a spectrogram, and then the spectrogram was transformed to MFCC gram, and the MFCC transformation gave the better results with noise insertion in the first phase. And this allowed us to, with the 91% accuracy, to detect that we can, in fact, tell people suffering from respiratory insufficiency from people not suffering from respiratory insufficiency in the case of COVID. So, and we actually, this was for respiratory insufficiency, but we also entered a competition. Sorry, I forgot to say these results I'm showing you were published in the Association of Computational Linguistics. We put the paper there. It's gonna appear in a few weeks from now. So this is a published work or to appear soon. And then we enter another competition. That competition provided us with data from COVID. So this was a COVID and non-COVID. And we showed that we can adapt our methods, our MFCC gram-based transformation using the data given by this competition. And we also had a paper accepted in this interspeech competition and lower accuracy. But this is already, we could beat the baselines given by the conference. So we have more or less almost 76% for identification form, voice, and coughs amazingly, we got the best result from coughs, but we never, our algorithms, they only deal with voice. They don't deal with coughs, but they seem to be applicable to coughs from this experiment. So this is just to show that our algorithms may be more, have broader application than simply respiratory insufficiency. So the research question that we started with was, is it possible to detect respiratory insufficiency from audio recordings? And the answer is yes, with 91% accuracy in COVID patients with respiratory insufficiency. Okay, this is our answer to this question. And then the next question, we never finish research. We always open new avenues. So the next research question is it possible to detect respiratory insufficiency in general? So in non-COVID patients, in anyone suffering from asthma or from heart disease or from blockage of the respiratory ways. And can we do that? And the answer, we don't know yet, but we are going to look for it. So in the future, we would like first to give the small data group, they are already starting to provide descriptions of the voice with people with respiratory insufficiency. So what's different from a normal voice from a voice with respiratory insufficiency? We have already interesting descriptions. There is a variation in the standard deviation of the fundamental frequency that has been very peculiar. We just try to describe that as well. And we have to answer this new research question I just mentioned, can we detect respiratory insufficiency in patients in general? We are starting a new collection phase with new triage experiments. So now we won't collect it from patients and from non-patients in different places. We will collect everyone in the same place, and the subject class will be unknown at collection time because it will be prior to diagnosis. And then we can say if we can deal with other pathologies that causes respiratory insufficiency, as I said, influenza, H1N1 and other kinds of influenzas. We can heart disease, lung problems, asthma, sleep disorders, etc. This all can cause respiratory insufficiency, and we're gonna know if we can detect them and if we can classify. We can say, well, this is 80% chance of being a heart disease, respiratory insufficiency. But these all take people to hospital. So in the first place, what's important for us to detect respiratory insufficiency in all those cases. So, and then we also would like to know if we can do further analysis on the signals we have. So what happens if we filter noise, if you look at the SHAP analysis and other techniques that are used with the neural networks. So that's what I had to present to you now. So this is our work at the moment in this avenue. So thank you very much, and I'm available for questioning. And if you want to contact me, please find my addresses there.
Results. I would like to remind the audience that you can ask questions in the chat, and we'll communicate them to Prof. Finger. And I have a question, actually several ones. First of all, what were the utterances recorded by the subjects? Was it spontaneous speech or read speech or?
It was a read speech. As you can see, this is what more or less what happened. This nurse or this student is showing a piece of paper with something written and recording from a cell phone in the head. So we have a very peculiar sentence that was designed by the linguists in our group to force the person to breathe several times in undetermined places. This is the kind of speech we recorded. For the new collection, we will have several kinds of things. We have a sustained vowel, we will have a nursery rhyme, something that has very clear points of breathing that we can compare with people with respiratory insufficiency and not. And we will also have a sentence similar to this one we showed. So the next phase will have 3 kinds of utterances that we're planning. But in this one, we only use the utterances that are being read by the person.
Thank you. And just a small question, another question is, did you deal or took care of the different severity in COVID in the patients? Were they like a homogeneous group, or were they in different stages of the disease?
They were in different stages of disease. We only took the voice samples from people suffering from respiratory insufficiency. So they had to have blood oxygenation levels below 92%, okay? Apart from that, of course, people in very severe conditions, they were in the internal, in the ICU, intensive care. So these people, we didn't have access. They couldn't speak.
Naturally.
They were, yeah. So we took people that had recovered, but not totally, and people that had the COVID, but not so severe. That's the only thing we could identify. But that's okay, because if we are looking at patient selection, triage, we want the people that can speak. They are still in doubt if they should go to the hospital or not. People that are in a very severe state, they just put them in an ambulance and take them to the hospital. Okay?
So thank you again, and we'll sure follow up this interesting research and compare notes. Thank you, Marcello. Have a wonderful day.
Yeah, thank you, and thank you very much, Toda Rabah, for the invitation. I'm out to be here.
Thank you. Okay. Last year in March, the ACLP was recruited to the national effort of detection or early detection of COVID. We divided into 4 groups. Each one of them tackled the task in different tools, different methods. And today, Aviad Malachi, researcher at the ACLP, will present our group's results in COVID detection from voice. Thank you, Aviad. תודה רבה, אביעד.
תודה ורד.
Thank you. Thank you for joining us. Please go ahead.
תודה רבה. And our research is called SARS-CoV-2 detection from voice. The reason it's called SARS-CoV-2 and not COVID-19 is because SARS-CoV-2 is the virus and COVID-19 is the disease. So we detect the virus, the presence of the virus, and not the disease. We did the research with alongside Sheba and Rabin medical centers, and with Mafat, the DDRD. At the time of the experiment 1 year ago, the current experiment we had, the previous research we had, was only on respiratory diseases and not on COVID-19. The only one we had on COVID-19 was the one that used symptoms only and not voice detection. Since then, other research used voice detection to detect COVID-19. The data set we used are mobile phone recordings from 88 subjects. 29 of them are positive and 59 of them are negative. The subjects recorded themselves in their smartphones, and at the time of the recording, they underwent PCR tests. Now, the results of the PCR tests was our labels. We used the results as targets for our research. The challenges, we had a few challenges in our research. First one was the data set, it was very small. The second one was the expression of the COVID-19 in the voice. So experts like medical doctors said that the patterns of the COVID-19 in the voice are very subtle, if exist at all. The solutions we had, the first solution was the use of semi-supervised training on a deep neural network, DNNs. Now, we trained the deep neural network, pre-trained, with external data set, speech data set. The second solution was the use of bootstrapping. We took segments. We cut each sample into segments, and then we got bigger data set. We made our data set more robust. The third solution was the use of classical and new regularization techniques. The approach we took is the use of three-stage architecture. The first one is the self-supervised transformer that was pre-trained on speech dataset, external speech dataset. The second one was the use of RNN classifier that was trained on our data that we gathered with the medical centers and the COVID-19 data. The last stage was the use of ensemble stacking to combine or fuse all the scores from the different classifiers we used into one score per speaker. The self-supervision architecture, stage one, we took pre-trained models that was trained by Mockingjay authors. They took the Libre speech data and fed it into an attention-based transformer. Now then, they fed it into a prediction heads to try to reconstruct missing frames. In our research, we took only the attention-based transformer and used it as a feature extraction, as a feature extractor. At the classifiers architecture, stage two, we took the COVID-19 data we gathered. We then fed it into the attention-based transformer. Then we combined it with the age and gender data of the speaker and the task data of the sample. All of that was fed into an RNN classifier, and the last layer of the RNN was the softmax layer that provides us with the probabilities of the positive class for each sample. At the end, we took the cross-entropy loss, we added it to novel SDR loss that was computed on the representations from the RNN. We had, we trained few classifiers, few RNN classifiers, each one of them with different hyperparameters and on different tasks. Much like human experts, we wanted each of the classifiers to be expert in the task. Now, we had two Z tasks and one A task. These tasks are manifesting differently on vocal cords or throat. The count tasks may hint on vocal fatigue. We also had one multidisciplinary task, the Z, the A, the cough, and the counting in one classifier. And all of these 7 classifiers we used in the next stage. In the next stage, the ensemble stage, we took the COVID-19 expert classifiers scores we saw before. Then we fed it into an hierarchical aggregation. Now, the results from the hierarchical aggregations, combined with the age and gender of the speaker, was fed into a linear SVM model. The results of this model was the final COVID-19 prediction scores. For every speaker, we had one score at the end. If, of course, the score was positive or negative, if it is positive to the COVID or not. The hierarchical aggregation had 4 phases. Phase 1, we took all the segments that we cut in the bootstrapping phase, all the segments of the same sample, and we combined them, we averaged the scores into one score per sample. Then, in the next stage, in the next phase, we took all the samples from the same task and combined their score, averaged their score into one task score. Then we converted it to features. For every speaker, we had few features. We used deep neural networks, so we needed to tackle the overfit problem. We did it with classical regularization methods, with some data robustness methods, and with novel speaker dissimilarity regularization SDR loss. The SDR loss was intended to create speaker invariant embeddings. So we penalize differences in the representations of each sample in the same class. So let me walk you through an example. We have on the screen a batch of 8 samples. 3 of them are of class 0 and 5 of them are of class 1. We calculated the L2 dissimilarities of class 0 with L2 dissimilarities between sample 1 and 2, 1 and 3, 2 and 3. Then we calculated between 4 and 5, 4 and 6, etc. We took all of these dissimilarities and then averaged it to one score and multiplied it by alpha. This was the SDR loss that then was added to the cross entropy loss to be back propagated into the network. We did some ablation analysis. We needed to make sure that every piece of our architecture was crucial for the goal. So we added the building blocks one by one. First, we connected the data to the softmax. The next experiment, experiment number 1, we added fully connected layer before the softmax. Experiment number 2, we added the GRU, the RNN layer, before the fully connected layer. In experiment number 3, we added the transformer, the pre-trained transformer before the GRU layer. And at the end, the experiment number 4, we added the ensemble stacking and the linear SVM. For performance evaluation, we used these classical metrics. So for the results, the ablation results, all of these results are F1 scores. We can see on the Z that the Z was the best task. It has 0.81 on experiment 3. The counting was the best improving task. It improved from 0.67 to 0.80. The worst task was the cough task. It wasn't improving at all, and we suspect it is because we pre-trained on a speech dataset, not on cough dataset. The expert results, we see similar things. The Z is the best task with 0.81 on the F1 column, and the cough is the worst with 0.58 in the F1 column. The multidisciplinary expert was doing pretty well. It was 0.79 on the F1 column. Now, for the ensemble stacking results, we chose to show the recall of 0.78. In this recall, the test was doing better from the cross-validation. So we have 0.79 F1 compared to 0.74. But it is because we only chose that point. If we see the full ROC curve, at the bottom, we can see on the right the cross-validation ROC, and on the left we can see the test ROC. And the cross-validation ROC is better than the test. It has AUC, area under the curve, of 0.81 compared to 0.63 on the test. We think that we got better results on the cross-validation because we had more data. On the test, we trained on 80% and tested on 20%, and on the cross-validation, we did leave one speaker out. So we trained on 99%. So to summarize it all, the goal was to detect COVID-19 from voice. The novelties in our research was the 3-stage architecture with the pre-trained transformer, the SDR loss, and the hierarchical ensemble stacking. The results of our study may imply the ability for correlation between the voice features and the SARS-CoV-2 detected by PCR. Thank you.
Thank you very much, Aviad.
Thank you.
And any questions from the audience? Okay, well, did you try to compare the addition of the SDR loss or to compare it to other diversity loss?
Yes, we tried a few other things, and we tried with SDR loss and with different alpha, if we remember the SDR loss formula with an alpha, and we got the best results with alpha of 0.1.
Okay. Thank you very much.
Thank you.
Okay. And our last speakers also joins us from the Southern Hemisphere. Mr. Nabil Sidat from the University of the Witwatersrand in Johannesburg, South Africa. Nabil has completed his first master at the University of the Witwatersrand and then went to a second master in Cornell and is now on his way to Cambridge to start his PhD. And Nabil will talk about, I should say, the other way of tackling speech data for medical disorders, which is the more classical, explainable machine learning. Hello, Nabil, and thank you so much for joining us.
Hi, Prof. Can everyone hear me okay?
Very good, thank you. Please go ahead.
Okay, awesome. Okay, so good evening, everyone. So I'll be presenting some of my work with my collaborators with Professor Verda Ronson and Yaniv Hamzani on automated and interpretable mHealth discrimination of vocal cord pathology enabled by machine learning. So before getting into it, I think it's prevalent for us to set a bit of context of what is the key clinical area that we wish to tackle and why this is an important clinical problem in the first place that both signal processing and machine learning methods can provide significant value for. And we aim to tackle the big issue of vocal cord pathology detection. And the prevalent clinical issue that we face is that fundamentally vocal cord pathology detection is largely very manual and very subjective. At the moment, clinicians often have to use methods such as laryngeal endoscopy. They have to have significant clinical insight. And this presents two huge problems when we think about it from a healthcare perspective. So firstly, we really need expert clinicians to be able to analyze these patients in order to give significant care and to actually treat patients correctly. But this can only be done once a diagnosis is made. But what this fundamentally also poses a challenge is in low-resource healthcare settings, where these clinicians are actually at a premium and patients often struggle to even see these clinicians with this level of expertise. And this actually just highlights the significant healthcare benefit that could be obtained through an automated solution for vocal pathology detection. So while previous works on the automated side, both from the signal processing and machine learning literature, have focused on this area, what we have noticed is that a big body of the work is targeted primarily at how do we distinguish between patients and controls. However, a neglected area is how do we distinguish within actual pathology itself, where in a clinical setting, a clinician needs to ascertain what type of pathology the patient is presenting with so that the correct treatment pathway can be initiated. And that's the area that we specifically aim to tackle, firstly by an automated mHealth solution, particularly targeted to low-resource healthcare settings. But additionally, we want to add explainable AI to this because we think that's a fundamental issue for clinical acceptability of such machine learning methods. So the contributions of our work are firstly presenting an automated assessment of different vocal cord pathologies, vocal cord polyp versus paralysis as a key clinical differentiator. Secondly, we present explainable AI and feature explainability in order to enable clinical utility of the methods that we're presenting. And finally, we've done work on a novel data set, which has been collected by easy-to-record smartphone recordings. And this is a preliminary study in order to motivate the further collection of such data sets by showing the merit on even such a small data set. And hopefully, this is a motivator to collect larger and more diverse data sets in this regard. So just at a high level in terms of the method that we have, so naturally we have a training pipeline, and when we think of clinical deployment, we are going to have an online e-health evaluation where a patient comes into a clinic. In terms of the actual training method, so we have a database of collected voice recordings from patients, which I'll be getting into in the next slide. We then apply very classical signal processing and machine learning methods to still highlight the value of these methods. And this is in terms of things such as windowing signals, typical feature extraction, and particularly motivated by the small data set size. We then do five-fold cross-validation, firstly to train the model. And once we've settled on the type of model, we can then train on the full data set. At deployment stage, where this would be in a clinic, a patient can then actually articulate into a smartphone to record the actual speech signal, where then a prediction can be made at inference time in a clinical setting in a very easy to use manner for a clinician. So in terms of the data set itself, so the data set is obviously the biggest challenge that we face in all healthcare studies pertinent to automation. And what we did was we conducted a study in a tertiary healthcare clinic where all patients signed an informed consent, and patients underwent 2-second voice samples of the R sound or the R articulation, and each patient had 3 samples taken per subject. So the rationale behind this articulation is that not only is it easy for a subject to perform, but additionally, this R articulation is very much language agnostic and therefore has utility across a variety of geographies, irrespective of language spoken in that geography. Secondly, when we talk about the number of participants, we had a total of 22 participants. So like we've said, this is a small study to motivate, but we still want to show that there's inherent value to be gained from this. So 22 participants having either vocal cord polyp diagnosed by an expert clinician or vocal cord paralysis. Of the divisions between these two classes, we had 11 subjects across both, and these were very broadly age-matched between the two classes. However, what was important was, at least from a class balance perspective, we did have balance there. What we also want to highlight from this is how did we go about stratifying these patients when we actually performed the model training. And because each subject carried out 3 samples, what we did want to make sure was that none of these samples from a specific patient leaked across into our testing set. And therefore, at the cross-validation, it was very much a stratified approach to ensure that each subject's individual recordings are still kept within a training set, and we never evaluate on that same subject, rather always evaluating on a different subject. In terms of the actual methods, and this is, I think, very much classical signal processing, classical machine learning, and this was fundamentally motivated by the dataset size being relatively small and still trying to demonstrate performance, but additionally from an explainability perspective. So in terms of feature extraction, given that we have a temporal signal, we did windowing of the signal and then extracted a variety of very common and widely used features, which typically come from the speech processing literature, things such as male frequency septal coefficients or MFCCs. We're looking at the spectral features of the signal, centroids, how fast is the signal changing, zero crossing rate, those sort of things. And I encourage people to have a look through the paper for more detail on this. We then try to approach a variety of classifiers because a priori, there's no way to know which classifier is the best. However, by exploring a variety of classifiers, we can then have some sort of understanding of what sort of decision boundary that we have in this type of data. And therefore, we explored a variety of classifiers from support vector machines to random forests to decision trees, etc. And more detail can be found in the paper. However, a big focus of this work that we really wanted to highlight was on the explainable AI. And that's in terms of Shapley values, deriving them value from game theoretic features, permutation, feature importance, as well as Morris sensitivity analysis was conducted. So just to highlight one of the models, and this is a result that was across the 5 folds as an average, was the best performing model of that of an extra trees classifier, and where we see both strong performance on the accuracy, but more pertinent to the clinical decision making is the strong performance that we see in the precision and recall scores that are obtained after the 5-fold cross-validation. We do want to preface this result saying we do acknowledge the dataset size being pretty small. However, we think this is a significant promising area and motivates not only the methods that we've applied, and we think that these methods are also highly generalizable as we start collecting more data. And I think that is the primary goal of this research. in terms of the actual explainability, which we think actually has the most clinical value to a clinician in terms of how do we facilitate better clinical decision-making from certain models rather than replacing a clinician, rather augmenting clinical decision-making through these results, is we conducted an evaluation, as I mentioned, with Shapley values, Morris sensitivity analysis, and feature permutation importance in order to highlight the most important features across the variety of methods which were important to this classification, and then working with our clinical partner to decide, are these features actually relevant from a clinical perspective? And what we firstly found was that MFCC type of features, as well as spectral contrast features, showed the highest importance. And what is significantly relevant about this is that all of these are tackling things in the frequency domain and actual explainability within the frequency domain. And where this ties into the clinical perspective is clinicians often look at these, obviously from a qualitative perspective, looking at frequencies of people's voices in order to make this distinction. So what we find this is it is highly interesting that the model is picking up on very similar sorts of features, and this warrants further investigation in future studies of how we can further tie this on the clinical side. So to discuss the results, so what we've proven is that we can provide an automated and explainable discrimination of vocal cord pathology, and we can do this in a very easy to use manner and in a very low cost manner using smartphone recordings. We've shown strong classification performance with the ExtraTrees classifier, and showing particularly from the feature explainability perspective that MFCCs and spectral features did show the most important and the most valuable to the classification. Finally, we've shown that accessibility of an mHealth system is vitally important and can be achieved with these sorts of systems. And what this can do from a clinical perspective is provide very early and very easy diagnosis. And what this can do is provide a very low-cost, patient-centered care, which is fundamentally what the healthcare system is after. In terms of future avenues of the research, is that what we aim to do is use the study as a building block to collect further data sets. As mentioned, firstly, larger data sets of both vocal cord polyp and vocal cord pathology and vocal cord paralysis, but as well as looking for more diverse data sets, whether it might be malignant versus benign lesions, the classification of other pathologies to augment this data set, and very pertinent right now, even respiratory diseases which affect vocal cords like COVID-19, because what this research has fundamentally demonstrated is that these very classical signal processing and machine learning methods do have strong utility in the speech processing format to provide a very robust results, but also results which are interpretable and can be deployed on highly accessible systems such as smartphones. Thank you. And if there's any questions.
Thank you very much, Nabil, for this wonderful talk. A question, you talked a lot about features. How about the classifier, and specifically comparing linear versus non-linear model? What do they suggest in the study?
So I think what the study specifically suggested when we looked at non-linear classifiers versus linear classifier is that fundamentally the performance actually wasn't even that different when these features were then projected into a non-linear space. And what we think this highly suggests is that at this point that the decision boundary in and of itself, where linear classifiers are still performing at high functionality, is that the decision boundary is actually fairly linear between the two classes of paralysis versus polyp.
Thank you. And in terms of attributes, we're on top of, again, the importance to classification of these features. What other attributes in these methods can be communicated to the healthcare professionals?
I think one area beyond just pure feature explainability that is particularly relevant to convey to a healthcare professional is what is the uncertainty in this prediction that's being made. And because we have multiple models, we can even make either ensembles of classifiers or have just pure probabilistic classifiers where we can then actually convey uncertainty, and that can actually help a clinician to decide whether to even use the model prediction in the first place or whether to defer to clinical expertise if the model is uncertain.
Thank you. Thank you very much. And as a last note or thought, this last year has shown us that the whole human race can suffer from the same problem, but the solutions are not distributed equally. And at the University of Witwatersrand, we engage a lot in finding really low-cost solution for Africa. And when I'm talking about low cost, it really should be very low cost, not in European or American standards. So definitely speech or voice-based analysis is one of the cheapest way to do diagnostics, and I think all our studies, and especially the studies in this session, are contributing to this goal. So I would like to thank all our speakers and to invite Dr. Itzik Lapidot for concluding remarks. Thank you, Nabil.
Thank you, Vered. I want to thank you all of this very interesting conference. I want to thank all the speakers and all the audience, and of course all the people that make this conference happens. And we hope to see you next year physically with us in Afeka at the next conference.
Thank you very much all for joining us, and hope to see you next year. Bye-bye.
Bye-bye.